Okay. Our purpose today is to prove that regular languages, NFAs and DFAs are all equivalent. Namely, if you're given a language by one representation, then you can represent it by the other representation. And some direction we already seen, right? So we saw that DFAs are essentially a special case of NFAs. NFAs accept regular languages. We saw that, right? Essentially, given a regular expression, we saw how to translate it into an NFA. And next, we're going to show that NFAs, given an NFA, we can generate a DFA that accepts the same language. And finally, we will see that how to extract a regular expression from an NFA. So in particular, our purpose here is to prove that given an NFA, we can compute an equivalent DFA. Okay. And so let's see what we have. We have a DFA, NFA, and regular languages or expression, right? Which are, essentially two different ways of writing the same thing, but they are the same, right? So we already saw that given a DFA, you easily can get an NFA because it's a special case. We saw that if you get a regular expression, you can get an NFA, right? And today what we will see is that given an NFA, you can get a DFA. And the other thing we are going to see is given an NFA, how to compute its equivalent regular expression, right? So this is today, and this is today. So I'm using maybe a different color. So once we prove those two red reductions, once we prove those two red reductions, right, we get that those three representations are equivalent. Given a representation in one form, we will get the other. Okay. So what's the idea of this reduction from NFA to DFA? So the important thing about DFAs is that they are memoryless, right? And in a given point in time, all you care about is what the current state is that the automata is in, but you don't remember and you don't care and you don't know how the automata got to this state, right? So the state is, all you know is what is here and now, right? Similar in spirit to this movie called Memento. And essentially, when we want to design a DFA, the real question we are asking is what's the minimal information that you need to remember and how to encode it as a state. Once we answer this, usually the DFA construction becomes very easy. So in the previous lecture, we saw how to simulate an NFA, right? So we're given this NFA and we simulated on the input ABA, and the idea was that we had this automata, and the idea was that for every state we had a light that said the NFA might be in this state if it's turned on, and it's definitely not in this state if it's turned off, right? And in the beginning we were in the state where, the state of the start state, that was the initial state. And here we handed the specific input AB, ABA. So on the input A, the NFA either move forward or stay where it is. So the next step after reading the A, the NFA might be in those two states, and it continues in this fashion, right? You enter the next input and you get that. So you get this sequence of machines, right? This is 1, this is 2, this is 3, This is 4, this is 5, this is 6, right? And that was this was the set, this was, here, this was the situation after the automata read all the input. And since the accept state was one of the possible locations of the automata, we said, well, yes, the NFA accepts this input, right? So if you think about it, what really, in any given point in time when we simulate the NFA, what information do we need, right? Or if we want to state it in a clear way, the state of the automata is the state that it might be in at any given point in time, right? What do I mean by that? At any given point in time, when we simulate the NFA, we have the set of states that it might be in, and that's the configuration that the NFA is in. This is the state of the NFA, right? So in a regular DFA, the state is really is the specific state, but in NFA, really, it can be a set of states. So in fact, let me call this a configuration, right? We have a configuration, which is in any given point in time, which is the set of states that the automata might be in, and then the NFA reads a character, or we simulate to the next character, the configuration changes into a new configuration, which is again a subset of the states. Now, if you think about it, what are the possible configurations? Well, any subset of the states is possible, right? So this is really the power set of the state of the original NFA. So the configurations are now member of the power set, right? So in particular, the number of configurations is 2 to the power of the size of the number of states in the NFA, right? And the idea now is that we can now take, since all the information we need in simulating the NFAs, the configurations, then the idea is now just take the configurations, treat every configuration as a state, and build a DFA on this configuration, right? Essentially draw a diagram showing how you move between configuration over inputs. And that's it. And what you will get is a DFA that would be equivalent to the original NFA. Right. So here's an example. It's a pretty silly example, but that's okay. We have an NFA that is this one. Clearly, this really accepts the language, any binary string that contains 1. This is the language of this automata. And now, let's draw a line. Right? On the right side now, we draw essentially, we write down all the configurations. Well, since there are 2 states, then the configuration here are going to be 2 to the 2, right? Every subset of those 2 states. So this is what we get here, right? Now, initially, the start configuration is the configuration. We just look we might initially be only in the start state because there are no epsilon transitions. So this is the start state, right? And now we just need to see what happened, right? So if we are here, for example, in Q0 and we get 0, then we can stay on Q0. That's the only thing we can do, right? So it's a self loop. Okay, on one or the other hand, we might stay in Q0 or we might move to Q1, right? So we move here, right? And similarly, if we're in Q0 or Q1, we're in both states. Since both of them have self-loop, we're going to stay where we are, right? Now, there are other 2 configurations, like the empty set and Q1. Those 2 configurations are not reachable from the start state, right? So, they exist, but they're not really relevant, right? So really what the answer is really this one. Of course, we can add disconnected parts are not that useful or interesting. Okay, so that's the big idea. And this is just what I just discussed, right? So let's skip that. Okay, now here's the more detailed example of the NFA we saw earlier, and the DFA that simulates it. Notice that every state here, for example, this one. Oops, maybe I should. Every state here. Oops. Every state here is just a snapshot of the NFA and the states that are on. Right, so we have one state here, we have one state here, etc., etc. You would, if you counted, you would notice that there is only 16 states here, but there should be 32, right? Because the original NFA have 5 states, so there should be 32 configurations. But the key observation is that here the start state has a self loop with all the inputs. So the start state is always going to be a possible location for the NFA to be in. So we need to consider only the configuration where this is present, which means reduce the number from 32 to 16, which is exactly the automata we got here. Right. The start configuration, by the way, is the bottom on the left here. Okay. So that's the basic idea of the how to do this conversion of NFA to DFA. The way to think about it is that we are simulating it. Once we're simulating it, all we care about in the NFA is the configuration, namely the set of states that the NFA might be in. And once we have that, we can just draw this configuration space with all the possible configurations, and we can draw transitions because they're uniquely defined, and we know what the start configuration is, we know what the accept configuration is. So configuration accepts if one of the states that are in the configuration are in the accept state of the original NFA, right? So we know what the accept state is. So everything is well defined. We got the DFA, and now we just run it on the input. Essentially what the DFA does, it just simulates the NFA on the input. So that was the big idea, or the sketch of the idea. And that's it.